Okay, so let's get started. So there are few basic concepts that you should be aware of. Okay, the first one is cyclicity of powers. The second one is arithmetic mean greater than equal to geometric mean greater than equal to harmonic mean. The third one is Cauchy-Schwarz inequality. The fourth one is factors and sum of factors. And then you have Fermat's theorem, right? So these are the basics that you should know to tackle problems on number theory. Okay, so now let's take one by one. So we'll start with cyclicity of powers. Now cyclicity of powers is very simple. This means that when you multiply a number with itself, it follows a certain trend. Now what is that trend? That trend is this: 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is power 1 raised to the power 1, 1 to the power 1, 2 to the power 1. Now power 2 is 1 to the power 2, which is 1, 2 to the power 2, which is 4, 3 to the power 2 is 9, 4 to the power 2 is 16, but we will just take the last digit, which is 6. 5 to the power 2 is 25, so we will just take the last digit, which is 5. 6 to the power 2 is 36, we will take the last digit. 7 to the power 2 is 49, last digit is 9. 8 to the power 2 is 64, last digit is 4. 9 to the power 2 is 81, last digit is 1. So if you look at the pattern of the last digit of this power 2, okay, before I continue, I would request everyone to attend the class on time from the next class onwards. It's very distracting if I have to click one at a time every 2 minutes. Okay, it completely distracts the flow of the class. So please be on time. Power 2, right? So if it is power 2, then the last digit is 1496, and then 1496 from the other end. So this is the pattern, and then you have a 5 in between. Okay, then you have power 3. So if it is power 3, then you have 1, then 4 into 2 is 8, then 9, 3, 27, 7, 6, 4, 24, 4, 5, 5, 5, 6, 6, 6, 9, 7, 63, which is 3, 8, 4, 32, 2, 1, 9, 9. So in power 3, you can see that all the digits from 1 to 9 have come back, but in different order. Okay. In power 2, you had 1, 4, 9, 6 and 5. So that means 2, 3, 7 and 8 are missing. So, which means that no perfect square can end in 2, 3, 7, 8. Remember this, no perfect square can end in 2, 3, 7, 8. Then you have power 4, where you have 1 and then 6, 7 3s are 21, 4 4s are 6, this is 5, 6, 7 3s are 21, 8 2s are 16, 9 9s are 81. So, in power 4 you have the pattern of 1 6 1 6, again 1 6 1 6, and then you have a 5 in between. And then if you go to power 5, then all the numbers will come back in the same order 1 2 3 4 5 6 7 8 9. So, therefore, if you look at the numbers 1, 5 and 6, they don't change. So, whichever power you raise it to, the last digit will be the same. So, 1 raised to any power will end in a 1, 5 raised to any power will end in a 5, 6 raised to any power will end in a 6. Now, the numbers which changes are the other numbers. Out of that, 4 and 9 follows a cyclicity of 4 6 4 6 4 6, and in case of 9 it is 9 1 9 1 9 1. Now, here also notice that 4 and 6 add up to 10, and 9 plus 1 add up to 10. And now you go to the other 4 numbers 2, 3, 7 and 8. Now, 2 has a cyclicity of 4, which is 2 4 8 6, and notice that 2 and 8, which are the last digit of 2 raised to power 1 and power 3 odd power, the sum of these two is 10. So, 2 plus 8 is 10, 4 plus 6 is also 10. So, 2 raised to the power odd will end in a 2 or a 8, 2 raised to the power even will end in a 4 or a 6. So, 2 4 8 6 is the cyclicity of 2, 8 4 2 6 is the cyclicity of 8. Now, notice here that 2 and 8 raised to an even power will end in the same digit 4 or 6. 8 to the power 2 will end in a 4, 2 to the power 2 will also end in a 4. 8 to the power 4 will end in a 6, 2 to the power 4 will end in a 6, right. So, 8 has a cyclicity of 8 4 2 6, 2 has a cyclicity of 2 4 8 6, and finally, we go to 3 and 7. 3 has a cyclicity of 3 9 7 1, and 7 has a cyclicity of 7 9 3 1. So, once again notice that 7 plus 3 is 10, 9 plus 1 is 10. So, which means that 2 3 7 8 has a cyclicity of 4, and 4 and 9 has a cyclicity of 2. So, that means any number ending in a 2 raised to any power, let us say any power, let us say 49, right. Now, any number ending in a 2 raised to power 49 will end in what number? So, in order to calculate this, what we have to do is we have to understand the cyclicity of this number 2. So, from the cyclicity table we can see that the cyclicity of 2 is 4, right. So, it repeats after every 4th power. So, that means this power 49 has to be divided by 4, and we have to take the remainder of this, which is 1. So, that means this number will be equivalent to a number ending in 2 raised to the power 1, which is 2. So, this number will end in a 2. Now, if instead of 49, if this is 48, some number raised to the power 48. Now, in that case, the remainder of 48 by 4 is 0. So, if the remainder is 0, then this will be equivalent to 2 to the power 4, which will end in a 6. So, this is how you calculate the last digit of a number. Okay. Please ask questions if you have any doubts on this. Okay.
Sir, please repeat again.
Okay. Yeah. Please stop me and ask if you have any doubts, because these are very, very important concepts. If you don't understand these, you will not be able to tackle problems. Okay.
Sir, this concept also 2686, sorry, 2486.
Yeah. I am repeating it from the beginning. Okay. So, look at the numbers from 1 to 9. Okay. Any number that we deal with is made up of these numbers. There is no other number, and the number 0, right. So, any number that we deal with ends in one of these, is comprised of one or more of these numbers. Now, how are these numbers behaving when they are raised to a certain power? So, for that you just need to understand each of the numbers. So, number 1 raised to power 1 is 1, 1 raised to power 2 is 1, 1 raised to power 3 is 1, 1 raised to power 4 is 1. Similarly, 2 to the power 1 is 1, 2 to the power 2 is 4, 2 to the power is 8, 2 to the power is 16, but we are looking at only the last digit, only the last digit. Okay. So, that means if I consider only the last digit, then the numbers would be 2, 4, 8, 6. Clear?
Yes, sir.
Okay. Similarly, now you look at 3. 3 to the power 1 is 3, 3 to the power 2 is 9, 3 to the power 3 is 27, which last digit is 7, 3 to the power 4 is 81, last digit is 1. So, the pattern is 3, 9, 7, 1. Similarly, 4, 4, 6, 4, then 4 to the power 2 is 16, last digit is 6, 4 to the power 3 is 64, last digit is 4, 4 to the power 4 is 256, last digit is 6. So, 4, 6, 4, 6. 5 and 6 will repeat itself. 5 to any power will end in a 5, 6 to any power will end in a 6. 7 will have 7, 9, 3, 1, 8 will have 8, 4, 2, 6, 9 will have 9, 1, 9, 1. Have you understood this now?
Yes, sir.
Okay. Now, if you have to calculate the last digit of any number raised to any power, for example, let me take a concrete example here. Let us say 392 raised to the power 487. Now, what will be the last digit of this number? That is the question, right. So, when you are dealing with this kind of a problem, then ignore all the digits except the last digit, just ignore rest of it. So, that means this is equivalent to 2 to the power 487. Clear up to here?
Yes, sir.
Ignore all the other digits except the last digit when you are looking for the last digit. So, this is equivalent to 2 to the power 487. Now, you know that the cyclicity of 2 is 2, 4, 8, 6. That means it repeats after every fourth power. Clear? Is it clear?
Yes, sir.
Okay. So, that means you have to divide this number, which is the power, by 4 and take the remainder of it. So, 487 by 4, remainder of this will be 87 by 4. So, this is 1, 2 and then 1 and then 3. So, the
3.
remainder is 3. So,
3.
this would be equivalent to 2 to the power 3, which is nothing but 8. So, the last digit of this number will be 8.
8. Yes.
Clear?
Yes, sir.
Okay. So, similarly, you can calculate the last digit of any power of any number if you know this rule. Okay. Okay. Now, let us take a slightly more difficult example. 373 to the power 581 multiplied by 292 to the power 679. What would be the last digit of this number? Now, by the same rule, all you have to do is ignore these two digits, just look at the last digit. So, 3 to the power 581 multiplied by 2 to the power 679. So, which will be the remainder of 581 divided by 4?
The 4 is the answer.
Yeah. So, 581 divided by 4, the remainder would be 1. So, this is 3 to the power 1 multiplied by 2 to the power 679. If you divide this by 4, the remainder would be 3. So, this would be 3 into 8, which is 24, last digit is 4. Clear? Everyone has understood this now? Please, please clarify if you have any doubts. So, this is the way that you calculate the last digit of any number. Okay. Now, how to calculate the remainder? For example, if I say what would be the remainder if I divide 5 to the power 91 divided by 6. What will be the remainder of this? What would be the remainder of this? Now, in order to do this kind of a problem, you have to understand one simple rule, right? And what is that rule? That rule is that if you divide any number by another number and you have a remainder, right, then that remainder will be the same when you go to its power, which means that remainder of this is equal to the remainder of 5 divided by 6 raised to the power 91. This concept is called congruence modulo. Okay? Very, very powerful concept. So, the remainder of any number divided by another number will be equal to the remainder of the base number divided by the same number raised to the same power. Okay. Now, now how do I calculate this? Now, in order to calculate this, you have to understand another concept. Now, you can write 5 as 6 times 0 plus 5. You know that any number can be written as divisor into quotient plus remainder. This is called remainder theorem or Euclid's division theorem, right? Basic theorem of mathematics. And you can also write this as 6 times 1 minus 1. Now, in your school you have been taught the first one, you have not been taught the second one, but the second one is actually more important. This is more powerful. So, if I use the first one, my remainder is 5. If I use the second one, my remainder is minus 1. So, this is called negative remainder. Okay. Now, this concept is very, very powerful when we are dealing with problems like these. So, the remainder of 5 by 6 can be written as minus 1 to the power 91. Now, minus 1 to the power to an odd power will be minus 1. So, that means this number will give me a remainder of minus 1 if I write it like this. But if I write it like this, the equivalent positive remainder would be 5. Why? Because whenever you get a negative remainder like this, you have to add it to the divisor to get the positive remainder. So, the actual remainder in this case would be 6 minus 1, which is 5. Is it clear? Is it clear?
Yes, sir.
There are a lot of questions asked in competitive exams based on what should be the remainder of this when divided by this. Okay. Okay. Suppose you don't know this rule. Suppose you don't know this rule. How will you crack this problem? So, the concept is, whenever I am trying to find a power like this, right, which I don't know, I suppose I don't know this concept of negative remainder, I don't know the concept of congruence modulo, then what am I going to do? Then I am going to do this. 5 to the power 91 can be written as 5 to the power 2 into 45 plus 1, right, which is 5 to the power 2 whole to the power 45 into 5. Clear? So, this is 25 to the power 45 into 5, and this has to be divided by 6. So, that means if I have to find the remainder of this, so remainder of 5 to the power 91 by 6 will be remainder of 25 to the power 45 by 6 multiplied by remainder of 5 by 6. Now, this is equal to remainder of 25 by 6 to the power 45 times remainder of 5 by 6 is 5. Now, what is the remainder of 25 by 6? This is 1. So, this would be 1 to the power 45 times 5, which is 5. So, you can do it like this also.
So technically there is no way you can escape the congruence modular rule, right?
No, you can't. That is the basis. So, if you don't know that, if you don't know this rule, then you can't do this. So, that's the basis. Okay.
Yes.
But the concept is, even if you don't know the negative remainder concept, the concept is you have to raise this, you have to manipulate this power in such a way that this number raised to a certain power divided by that number 6 will give you a remainder of 1 or 2. Okay. So, that is why I raised it to the power 2, because 25 by 6 is remainder is 1. That is why I did it like this. Is it clear? Let me take another example. What will be the remainder of 7 to the power 84 by 100? What will be the remainder of this? Can anyone crack this? Try using this rule, this concept. So, 7 raised to some power divided by 100 will give a remainder of 1 or 2. Now, since you know negative remainder concept, it can be plus minus 1 or 2. Okay. So, what will that number be? So, 7 to the power 2 is 49, 7 to the power 3 is 343, and 7 to the power 4 is 2401.
So I think 1 is the answer.
Correct. 1 is the answer. 7 to the power 4 is 2401. So, 7 to the power 4 divided by 100 will give you a remainder of 1. So, this is 7 to the power 84. So, you can write this as 7 to the power 4 to the power 21. This number divided by 100 will give you 1. So, this is 1 to the power 21, which is 1.
Sir,
Yeah.
I have done it like this way. Like I have fragmented 7 to the power 84 in 7 cube whole to the power 28 divided by 100.
Okay.
And then applying the congruence modular formula, like 43 to the power 28. So 3 to the power 28, it's just 3 to the power 0 is which is 1.
No. So, you have done
Like 7 cube by 100,
I got it.
which is
343 to the power
343
20.
by yes. Here
Right.
43 is
By
the remainder.
43 is the remainder, correct?
Like 43 to the power 28. So 28 is divisible by completely 4. So it's technically 3 to the power 0, which is 1.
But this is not entirely correct. In this case, it matched. But see, when you are doing, see, understand this one thing. 43 by, so this is equivalent to 43 by 100. The remainder of 343 by 100 is 43.
Yes.
So
yes,
43 by to the power 28 by 100. Now, fortunately for you, in this case, it just incidentally it came out as 1.
Ah, right.
But it could be 21, it could be 31, it could be 61, it could be any number ending in a 1 less than 100.
Right.
Clear?
Yes.
So, remember this, that the absolute remainder should be 1, not like this. This is wrong. In this case, it just matched by by chance, but that's not the way to do it.
Yes.
Okay, so this is how you find the remainder of a number divided by another number. Is it clear? Everyone clear?
Yes, sir.
Okay. Let's look at another case. Okay, let's look at a simple example. 3 to the power 4 divided by 5. What is the remainder? This is simple. Remainder is 1.
1.
Okay. 2 to the power 4 divided by 5. Remainder?
So 1.
1. Okay. 2 to the power 6 by 7. Remainder?
4.
64 by 7. Remainder is 1.
Oh.
Okay. So, this means that if I have a number excuse me, a to the power p by q, a to the power, not p, a to the power q minus 1 by q, remainder of this will be equal to 1 if q is dash. What is q? Can anyone say what is q?
The q is 4n plus 1.
No. Q is a prime number. If the denominator or the divisor is a prime number and the power is 1 less than that, then a number raised to that number will give you a remainder of 1. Clear? Is it clear?
No, sir. Please repeat.
Okay, let me go back to the examples again.
Sir, could you please repeat the remainder of 2 to the power 6 by 7, which is 1? I actually tried to apply the congruence modulo, and it's 2 by 7 whole to the power 6, right? So 6, when it's divisible by 4, uh,
It is 2 by 7, that means the remainder is 2. If you are doing congruence modulo, the remainder is 2,
yes, sir.
right?
Yes. So it's 2 to the power 2, right?
Why 2 to the power 2? You are mixing up two things. You are mixing up power, cyclicity with congruence modulo.
Oh, yes, yes, yes. Sorry, sir.
Congruence modulo is a different thing.
Mhm.
Cyclicity is
Sorry.
different. You're
Right.
actually you're getting mixed up with it. Okay.
Yes, yes.
Let me repeat the examples. The remainder of 3 to the power 4 divided by 5 is 1. 3 to the power 4 is 81 by 5. Remainder is 1. Remainder of 2 to the power 4 by 5. 16 by 5 is 1. 2 to the power 6 is 64 by 7. 1. Now these numbers are all prime numbers, right? And you can see that, and you can try it with any number. Okay, raised to the power has to be 1 less than the denominator, than the divisor, right? That will give you a remainder of 1. Okay, this rule is called Fermat's rule. Okay. Okay, simple as this. So if you see a number in the form of a to the power q minus 1 by q, where q is a prime number, that means the divisor is a prime number and the power is 1 less than the prime number, then the remainder will be 1. Clear? Whoever asked that question?
Yes, sir.
Okay, there was a lady who asked the question. Is it clear for you? What is the rule?
Yes, sir.
So all you have to do is observe the divisor, whether it's prime or not. Okay. Now let us look at an example which is slightly more twisted. Okay. Okay. 7 to the power 130 by 131. What is the remainder of this? The remainder would be 1, because 131 is a prime number. 130 is 1 less than this. So if you apply Fermat's rule, simply the remainder is 1. But you cannot do this kind of a problem using congruence modulo. It will be difficult. I mean, you can, but it will take time. Is it clear? Is it clear?
Yes, sir.
Okay. So these are two very important rules, congruence modulo and Fermat's theorem, to deal with problems on remainders of numbers. Okay. Next we go to factors. Oh, before I go to factors, since I already introduced the concept of negative remainders, now this concept of negative remainder is a very, very powerful concept, and there are certain problems which you cannot solve if you don't know this concept. I gave you one example, right? Right? The example that I gave, actually you can do, because I showed you the other way. So you can split it up into combination of other powers, and you can apply congruence modulo and you can solve it. But there is another problem, very simple problem, which you cannot solve if you don't know this. Okay, let me ask you this question. uh, what is the least two-digit number which when divided by 3, 4 and 5 gives a remainder of 1 in each case? What would be the answer? This is a class 6 problem. Least two-digit number which when divided by 3, 4 and 5 gives a remainder of 1 in each case. Anyone? Very simple.
61.
Correct. And how did you do it?
LCM plus 1.
LCM plus 1. Perfect. So all you have to do is take the LCM of 3, 4, 5 plus 1, which is 61. Now let me give you the same problem, but there is a small twist. List two-digit number which when divided by 3 gives a remainder of 2, divided by 4 gives a remainder of 3, and divided by 5 gives a remainder of 4. List two-digit number which will give a remainder of 2 when divided by 3, 3 when divided by 4 and 4 when divided by 5. What will be the answer to this one? Anyone? Obviously, the concept is same, LCM plus whatever the remainder is. But here the problem is that the remainders are different, right? You can add the remainder only if the remainders are same, isn't it? Now, in order to solve this problem, if I don't know the concept of negative remainder, what will I do? I will take each case one by one. Number which gives a remainder of 2 when divided by 3. What are the numbers? The first number is 2. The second number is 2 plus 3, 5. Then 8, 11. All these numbers will give a remainder of 2 when you divide it by 3. The second series starts with 3, 3 plus 4, 7, 7 plus 4, 11, 11 plus 4, 15 and so on. The third series starts with 4, 4 plus 5, 9, plus 5, 14, plus 5, 19 and so on, right? Now, that means there has to be a number which will be common to all these three, right? And I have to figure that out, right? Now you can see that all these three are in AP series, arithmetic progression, right, where the common difference is same. So, the first number that I can see common between the first and the second is 11, right. Now, in the second series, the next number would be 19. So, the first number that I can see common between the second and the third is 19, correct, right. So, let us expand these two series, 2, 5, 8, 11, then 3, 14, 17, 20, 23, and then 26, 29, 32, etc. Then I have 3, 7, 11, 15, 19, and then 23, 27, 31, 35, 39, etc. And then I have 4, 9, 14, 19, 24, 29, 34, 39, etc. So now if I start identifying the numbers which are common. So the first number I can see common between the first and the second is 11. The number common between second and third is 19, and then I can see 23, which is common between the first and the second, and then I can see what is the next number? 39, right? 39, which is common between the second and the third. Now if I want to do it this way, of course I can use a arithmetic progression formula, it will be a little more faster, but I'm just trying to explain you the concept. So if you look at this, then in the first series, after the first number 11, which is common with the second one, the second number which is common with the second one is 23, which is 1, 2, 3, fourth number from this one, and this is the third number from this one, right? Now the common difference of this series is 4, and the common difference of this series is 3. So it is just the reverse. So the common difference of this series will be the number of terms after which the second number will match, right? The same logic applies in the second case. So the common difference of the third series is 5. So after the first one matches with the third one, the fifth number from there, 1, 2, 3, 4, 5 will match with the fourth number in the second series, right? Clear? Okay. So that means I have to take the LCM of 4 and 5, which is 20, right? Clear? Understood?
No, sir, please repeat.
So look at the first series. The first number which is common with the second one is 11. The second number which is common with the second one is 23. Now, how many numbers are there between 11 to 23? 1, 2, 3, 4. 23 is the fourth number from 11 in the first series. 23 is the third number from 11 in the second series. Now, just look at these two series, right? First and second. 11 and 23. The difference between 11 and 23 is 4 numbers in the first series and 3 numbers in the second series. Now, how does it? Why is it 4 and why is it 3? Because the common difference of the second series is 4, which is the number of terms here, and the common difference of the first series is 3, which is the number of terms here. Now, is it clear?
Yes, sir. Sir, I was not clear with the part where you said we have to take the LCM of 4 and 5, that is 20.
No, I skipped a step actually. So actually, now if I want to do it like this, so that means I know that now let me concentrate on the first two series. So I know that the fourth number of the first series, every 4 numbers will coincide with the second series. So 23, and then I have 32, and then I have 35, 38. So 1, 2, 3, 4, 35 should match, right? So it goes on like this, right? And in the second series and third series, the fifth term of the second series matches with the fourth term of the third series, right? So that means 39, and then the fifth term will be 39 plus 4, 43, then 47, 51 into 3, 55 and 59, and the fourth term here would be 39, 44, 49, 54, 59. So 59 matches between the second and the third series, correct? Right? Now the difference between 39 and 59 is 5 terms in the second series, right? Now I go back to the first series. So I had 35 and then every fourth term matches. So that means 59 minus 35 is 24, divided by 4 is 6. So that means that is divisible. So here also I will have 59, which will be the answer. Clear? So it's the LCM of 4 and 5, that is 20. So if you take 20 starting from 19 is 39, then 39 to 59, right? Here also 19, 39, 59, right? So that these are the numbers which will match in the second and the third series, right? And the LCM of 3 and 4 is 12, right? So it starts with 11, 11 plus 12 is 23, 23 plus 12 is 35, 35 plus 12 will be 47, that will again match with the second series, and then 59. Now you understood why I said LCM?
Yes, sir.
So which means that if I know the common difference, so the simplest way of doing this is, instead of doing all of this, I just write the three series and I just identify the first terms which are equal between the first and second, second and third. This is a layman's way of doing it, right? And then I look at the first and second series and I see the common difference, 3 and 4. I take the LCM, 12. So I just keep adding 12 with 11. So 11 plus 12 is 23, plus 12 is 35, 47, 59. So this will be common between the first and the second. Now I go to second and third. LCM is 20, 4 and 5. First term which is common is 19. So I write 19, 39, 59. So this is the answer. This is a layman's way of doing it. Okay. If I have to do with arithmetic progression, I will write the equation and solve it a little faster. That I will do when I do APGP, right? But let me come back to the problem. So obviously this is not the way that I should be solving this kind of a problem, right? So what should be the way? So the way is very simple. I will apply the same rule that I did that I applied in the previous case. So I will simply find the remainder in each case. Remainder of 2 when it divides by 3 means a number 3 can be written as 2 into 1. Oh, sorry. A number 2 can be written as 3 into 0 plus 2. It can also be written as 3 into 1 minus 1. So a remainder of plus 2 is equivalent to 3 minus 2, 2 minus 3, which is minus 1. So that means the equivalent remainder is minus 1. Here also the equivalent remainder is 3 minus 4, which is minus 1, 4 minus 5, which is minus 1. So now if I apply the concept of LCM of 3, 4, 5 is 60 and I add minus 1, the answer is 59. Now which way is faster? Now if you don't know the concept of negative remainder in this case, you have to do it the way I showed, or you can apply the formula of arithmetic progression, but that still will take more time than by doing this. Is it clear? Has everyone understood the concept of negative remainder?
Yes, sir.
Very, very powerful concept in solving problems. So if you know the concept of negative remainder, then you can solve problems on remainders, on LCM, and many other kind of problems where It involves remainder concept. Okay. The last concept that I am going to introduce today is factors. Okay, before I go to factors, there is one more thing to discuss. Okay, everyone is aware of the concept of real numbers, because before I go to factors, the concept of real numbers should be clear. Everyone knows what is a real number? No?
Yes, sir.
What is a real number?
So anything between minus infinity to plus infinity.
No, that's not a definition of a real number. What is the definition of a real number? The definition of a real number is that the square of a real number is always greater than or equal to 0. This is the definition of a real number. Once again, a very powerful concept. Okay. Now, real numbers are divided into two types, which are rational and irrational. What is a rational number? What is an irrational number?
Sir, any number which can be expressed in terms of p by q, where q not equals to 0 is rational.
No. Again, there is one more thing that is missed out. One more condition, which is
P and q
HCF of P and Q will be 1.
is 1. Yes, yes, yes.
It has to be relatively prime.
Right, right, right.
Okay. And what is the definition of an irrational number?
So the number which is not rational is irrational.
This is just one definition. What is the second definition? This is the first definition of.
Cannot be expressed in terms of p by q.
This is the first definition of a rational irrational. The second definition is a rational number always has to be a terminating decimal or a recurring decimal, one of these. Okay. It has to be either terminating or recurring, one of these two. And an irrational number will be non-terminating and non-recurring. Clear? This is the second definition. For example, if you look at the number pi, now you look at this number 3.14159265, whatever, there is no repetition, right? But if I take the number 1 divided by 3, this is 0.3333. This is called recurring, the other one is called non-terminating, non-recurring. This is the difference. So that is why pi is
Irrational.
irrational. Now we write pi as 22 by 7. Now 22 divided by 7 is this. Now this is by definition a rational number. It is a repetition of 142857. Right? Clear? So 22 by 7 is an approximation of the number pi. The actual number pi is this, which is not equal to 22 by 7. Okay. So these are the two definitions of rational and irrational numbers. Okay. Now then, rational numbers can be divided into integers and fractions or decimals. Now integers can be divided into negative, 0 and positive. Positive integers are called
Natural numbers.
natural numbers. 0 and along with positive integers is called whole numbers. right? Fractions are of three types: proper, improper, and mixed. Proper means where the
P is less than Q.
numerator is less than the denominator. Improper means numerator greater than denominator. So, this is always less than 1, this is always greater than 1. And mixed means an integer plus a proper fraction, right? Improper can be expressed as mixed, mixed can be expressed as improper. And finally, we come to decimals. Decimals are of two types: recurring, terminating and recurring, recurring and terminating, right? Now, what gives rise to a terminating decimal? What gives rise to a recurring decimal? Anyone? What makes a decimal recurring? What makes a decimal terminating? Now, the concept of decimal came from division by 10 or powers of 10, right. So, that means if I have to have 10 or power of 10 in the denominator, then it will be terminating, simple. Like for example, 1 by 2. Now, 1 by 2, I have a 2 in the denominator, I can make it into 5 into 5. So, this becomes 5 by 10. So, this becomes 0.5. So, division by 10, 10 is nothing but 2 times 5. So, that means I need to have 2 or 5 in the denominator. It can be combination of 2 and 5, right. For example, if I have 1 by 4. Now, this is 1 by 2 square. So, I can multiply with 5 square into 5 square, this becomes 25 by 100, which is 0.25. If I have 1 by 20, so this is 1 by 2 square into 5. So, I need one more 5 down there and I multiply with 5. This becomes 5 by 100, which is 0.05. This is the logic of terminating decimal. So, if my denominator contains 2 or 5, then it will be terminating, right. And the number of digits after the decimal will depend on the power of 2 and 5. Number of digits will depend on the power of 2 and 5. Clear? Is it clear for everyone?
Yes, sir.
Okay. So, can you tell me 1, 2, 3, 4, 5, 6, 7, 8, 9 by 160? Will this be a terminating decimal or not? And if it is terminating, then how many digits will be there after the decimal point? So, in order to determine whether it is terminating or not, you have to factorize the denominator. 160 is 2 to the power what? Into 5 to the power what?
Sir, 5.
2 to the power 5, 5 to the power 1, right. So, that means it has only 2 and 5. So, it will be a terminating decimal for sure, correct. Okay. And the number of digits after the decimal point will be 5. So, the answer whatever will have 5 digits after the decimal point, because the power of 2 is 5 here. So, this is how you determine whether a decimal is terminating or recurring. And finally, before I end, recurring decimal 1 by 3. This is recurring, 0.3 recurring. 1 by 6. This is actually 1 by 2 into 3. I have a 2 here. So, you can ask me, there is a 2. Why is it recurring? Because the 2 is there, fine, but then I have a 3. So, if there is anything other than 2 and 5 in the denominator, the decimal will be recurring. And actually, this is 0.16 recurring. There is one digit which is not recurring, and this is because of the 1, 2. Okay. Clear?
Yes, sir.
Okay. The last thing before I close is in that, and in the next class I'm going to show you the conversion of recurring to fractions, which is again very important in dealing with problems. The last thing is, if I have a number 1, 2, 3, 4. Now, this number is actually 1 into 1000, that means 1 into 10 to the power 3 plus 2 into 10 to the power 2 plus 3 into 10 to the power 1 plus 4. So, any number in the decimal system is written like this, because the base is 10. Clear? The base is 10. Right? Okay. Now, if I have a decimal like 0.1234, how will I write this? This would be just the opposite, 1 into 10 to the power minus 1 plus 2 into 10 to the power minus 2 plus 3 into 10 to the power minus 3 plus 4 into 10 to the power minus 4. Okay. Okay.
Yes, sir.
And based on this, can you tell me the division rule for 7? Does anyone know this? Division rule for 7. For example, if I have a number, I'll give you a simple example so that you can test it out. 51. This is not divisible by 7, right? Now, how do I write this? I write this as 5 into 10 plus 1. Correct? Right? 49. This is divisible by 7. This is 4 into 10 plus 9. Correct? Yes, no?
Yes, sir.
Now, how am I going to test whether a number is divisible by 7 or not? The way to test is just replace the 10 with 3. So, just write this as 5 into 3 plus 1. This is 4 into 3 plus 9. This is 12 plus 9, 21. This is 15 plus 1, 16. Now, 16 is not divisible by 7, so that is why this is not divisible by 7. 21 is divisible by 7, so 49 is divisible by 7. Now, you can ask me, why am I replacing the 10 with 3? I am changing the base of the number from 10 to 3. Why am I doing this? Because 7 plus 3 is 10. So, when I am testing for divisibility by 7, I have to change the base from 10 to 3. This
Sir, can the same rule be applied for 3 as well?
Any number.
Like if I...
Any number.
Okay.
Any number. You can use this rule for divisibility by 13. 13
Okay.
is, sorry,
Like,
13 minus 3
1
is
into
10.
10?
13 minus 3 is 10. So, when you are checking
Right.
for divisibility by 13, you have to change the base from 10 to minus 3. In case of 7, it's 10 to plus 3. In case of 13, it's 10 to minus 3. So, you can check it out. Take a number 65. This is 6 into 10 plus 5. Change the base from 10 to minus 3. So, 6 into minus 3 plus 5, which is minus 18 plus 5, that is minus 13 divisible by 13.
Okay.
These are not written in any textbooks. Neither will you get it on Google. Okay. So, so these rules are very important. These concepts are very important when you are dealing with numbers. So, a combination of these concepts will help you deal with problems on number theory. Now, I haven't yet started problems on number theory. This is basically the first class or the second class, I think. No, second class, right? So, in the last class, I gave you some flavor of the problems that you can expect, but now I have started from the absolute basics. Okay, and these are basics which you have to be aware of in order to solve problems. Okay. Now,
Sir,
yeah.
sir, before we end, like, can you please give us some examples on the remainder theorem, like whatever you have covered today? We'll try to solve that out, and we'll show you next week.
Examples of remainder theorem, right?
Like on the congruence modulo, like whatever you taught today,
Okay.
based upon those.
Let me. Okay. Okay. Let me. Okay. I'll give you. Let me check.
Okay,
One
sir.
second. One last thing before I end, because these are all related concepts. Okay. If you are trying to find multiplication of numbers, okay. Let's say you want to multiply 88 into 93. Can someone tell me the answer without multiplying? These concepts are very powerful because you have to deal with numbers like these, especially
Say 8184.
81.
84.
Okay. Can you explain how you did it?
Sir, I have fragmented 88 into 8 into 11, multiplied 93 with 8, and then
No.
multiplied with 11.
No, I said without multiplication. Not. That's not the way.
Okay.
I mean, obviously, what you have done is correct, but I was not hinting at that. Now, the reason I'm showing you these kind of things is because when you deal with problems, you have to in lot of problems you deal with percentages, or in compound interest problems you deal with numbers close to 100, right? 105 into 106, like that, right? Or 93 into 88. So the rule is very simple. So 88 is, how far is 88 from 100? 12.
12.
93 is 7 from 100.
7.
So if you cross add any of the two pairs, 88 minus 7 is 81. 93 minus 12 is also 81. And then you multiply these two numbers, minus 12 and minus 7 is 84. So 8184 is the answer. So basically you don't do anything, you just look at the numbers and mentally you calculate, oh, 93 is 7 away from 100, so 8 minus 7 is 81, right? 81. So 7 into 12 is 84, that's it. Clear?
Yes, sir. Yes.
Okay. If it is more than 100 also, it is the same rule. Let's say
Just plus.
106 into 112. So plus 6 plus 12. So this would be, cross at any one pair, 118 and 6 12s are 72. 11872 is the answer. Okay. Now, what will you do in this case? 86 into 83. What will you do in this case? This is minus 14, this is minus 17. So the first part will remain the same. 83 minus 14 is 69. and minus 14 into minus 17 is how much?
238.
238. Now, when you get 238, you have to write the 2 above 9 and then 38
Yeah.
and then add it up.
8138.
7138. Oh, sorry, 8138, correct.
Yes.
8138, right.
Hmm.
No, it's not 8138, sorry. 7138.
7138, sir. 7138.
Yeah. Clear? And if you have one number more than 100, one less than 100, 3 times 91. So this is plus 3, this is minus 9. Once again cross add 9, 4 and then multiply these two. Now this gives you minus 27. Now if you get minus 27, what you have,
9373.
you have to add 2 zeros and subtract 27 from there. That's it. So 9373.
73.
Correct. So this is a very simple method and very powerful method to multiply numbers which are close to 100, 10, 1000 or any powers of 10. Okay, clear?
Yes, sir.
Okay, you wanted problems on remainder theorem. Just let me check if I have.
So you can send PDF as well if you have like.
Just give me a
You
second.
know,
Okay, I don't have it ready-made in terms of remainder theorem like that. It will be a mixed bag. Okay, I'll need to check this out. I'll send you later. Okay.
okay, sir. Okay. No issue, sir.
I don't have it right now. I don't have it ready
Yes,
made,
yes.
so I'll send it later.
Sure, sir. Sure.
Okay.
Yes.
Okay.
sir.
So that's all for today, and we meet again next week. Okay. Take
Thank you,
care.
sir.
Bye.
Thank you, sir.
Thank you, sir.
Okay, sir.